Hi there. Welcome back to the Ephemeris podcast. I'm your host, Aphelion, and I apologize about the whole situation last Sunday. The reason why I didn't post it immediately after the internet outage was just to make sure that um, I didn't have any missed episodes in the future, or at least, I try to avoid that with getting caught up on doing 2 or 3 episodes worth of research work. But today's episode, as has been long awaited, is about Kepler, possibly one of the most influential astronomers, period. And if there's one astronomer you're guaranteed to learn about when you study astronomy, it is Kepler. So that says quite a lot about his influence if you don't believe me. So let's talk about him. Kepler was born in 1571 in Weil der Stadt in modern-day Germany, and I apologize if I get any of the pronunciations in today's episode wrong, because as you probably know if you've been listening for a while, my accents are not very good when it comes to foreign languages like German. So yeah, Weil der Stadt was near Stuttgart and Göppingen, which you'll remember from last episode, hopefully. And side note, being born in 1571 turned out to be quite fortunate for Kepler because he got to witness the Great Comet of 1577 as a child. I can't think of anything that would be equivalent to that. I do know that there is a comet that wouldn't come for 6,000 years that came in 2020, but I don't think that really holds a special place in many people's hearts. So, yeah. Anyways, getting to witness the Great Comet of 1577 as a child was a great thing, and it turned out to be great for Kepler. He was not born into immediate nobility as some other people have this season. Um, with Maestlin and Tycho being from a Danish noble family. Not so much the situation for Kepler. His family was poor by the time he was born, and he ended up with poor eyesight, which would imply that he wouldn't be quite as proficient as Maestlin would, with identifying 11 stars in the Pleiades cluster. But Kepler was still very much distinguished at a young age. He attended Latin school and enrolled at a Protestant seminary in Heidelberg in 1584. But then, after 5 years, matriculated to, you guessed where, to Bingen University. And he happened to learn about Copernicus, but we know who's responsible for that, don't we? Even though Kepler accepted a position as a math teacher in Austria, Kepler and Maestlin continued to join forces through the creation of Mysterium Cosmographium in the 1590s, so nothing new there. But there's a nice quotation that didn't quite fit into last episode that works great here, because it's about Kepler being under the influence of Maestlin. So the quote goes something like this. With the help of Maestlin in 1595, Kepler believed that he had discovered the relationship between the planets, period, and the distance from the sun. He did so by first assuming equal velocity for each planet and then observing that the planets did not just revolve around just according to the length of their radii. Kepler observed that the sun exerted a force that was progressively attenuated as planets are farther and farther away from the sun itself. Maestlin even provided the geometry to help visualize Kepler's theory of the sun force and its effects on other planets. So that's a little bit of a sneak peek into what Kepler's going to find out, but as you can tell, there's a little bit of Maestlin in there, kind of helping him out with geometric things and visualizations. So, yeah, another detail about the relation of Maestlin and Kepler that makes a great plot twist in this episode is the fact that Maestlin cut off communication with Kepler around 1600 under the fear that Kepler would make their communications through letters public. And coincidentally, perhaps I'm just making a very unnecessary situation out of this. This is around the time that Kepler moved to Prague to work under Tycho and create the Rudolphine Tables, which was a new star catalog. But yeah, I wanted to save that kind of Maestlin-Kepler communication cutoff for this episode because, suspense. And it's probably ridiculous to correlate these two occurrences. But if you do, it kind of feels like there's a little bit of a love triangle going on with Kepler, Maestlin, and Tycho. Not in, a very extensive way. I'm using the term love triangle very lightly. It seems like the biggest influence on Kepler is split between Maestlin and Tycho, who are working independently as contemporaries of each other. And yeah, again, it's extremely ridiculous to assume such a thing, but it's just a fun little tangent. Um, yeah, so when Brahe died, or Tycho died, Kepler took his position and his title, as I believe we talked about in Tycho's episode. If we didn't, then that is new information to you. He spent the early 1600s working on multiple things like Astronomia pars Optica, which, as the name suggests, he worked on optics in that sort of writing. He worked on observing the supernova of 1604, which is now Kepler's supernova remnant. He worked on Stella Nova, which had to do with that supernova, and he worked on some other astrological and chronological work. Now, in 1609, he published Astronomia Nova, which is going to be a bulk of what we talk about today, and that's going to contain 2 laws of planetary motion that are named after him in current day. In 1619, Kepler published Harmonices Mundi. Again, it's Latin, so that's just inherently going to be difficult to say. He laid out the 3rd law in this work, and we won't really talk about it. I'll give a quick summary soon enough. The following year saw the publication of his 7-volume Epitome, Astronomiae, in 1621, an influential work that discussed heliocentric astronomy in a systematic way. And this is, just to be clear, different from the Epitome that Maestlin published. And I think, as we'll talk about in just a moment, Kepler did take some inspiration from Maestlin's Epitome. So yeah, his later life after that was just a bunch of political matters, religious matters, which don't have much to do with astronomy. So we're going to cut off the biography right there and get into the juicy part of the episode, which is the astronomical work of Kepler. As a preface, there are works of Kepler's that I will not discuss deeply. There's Stereometrica Doliorum, which establishes basic integral calculus through, I think, some volume problems, probably like optimization problems, as you would see in a typical high school calculus course. It's going to be common to see mathematics and astronomy join forces, I think, in future episodes. We've kind of seen mathematics evolve with astronomy, with Greeks mastering geometry, Euclid's Elements having some influence. We've seen trigonometry through kind of Tycho's little algorithm or method. But we will soon see some developments in calculus alongside physics and astronomy. I mean, if you just think about Albert Einstein, he did quite a lot of math with the amount of physics that he did. So yeah, I think that's going to be an inevitable part about some of the episodes later on. And then there's the one that I just talked about, Harmonices Mundi, which, although it has a 3rd law, is mostly an attempt of Kepler's to impersonate Philolaus by relating harmonics with physical phenomena and discussing geometrical congruences. So there's not a whole lot to bite off when it comes to that. So here we go. Let's get into some stuff that we should talk about. In 1595, while teaching a class, Kepler experienced a moment of illumination, and this is sort of information that has been elegantly put online that I'd just like to reference here. It struck him suddenly that the spacing among the 6 Copernican planets might be explained by circumscribing and inscribing each orbit with one of the 5 regular polyhedrons. Since Kepler knew Euclid's proof that there can be 5 and only 5 such mathematical objects made up of congruent faces, he decided that such self-sufficiency must betoken a perfect idea. And just to be clear, the 5 regular polyhedrons are not new at this time. If you don't know what the 5 regular polyhedrons are, they are the tetrahedron, which is pretty much pyramid, a cube, an octahedron, a dodecahedron, which is I think 10 faces, octahedron being 8, and then icosahedron, which is 20 faces. And they're shapes that were discovered during the time of the Greeks and was analyzed by Euclid. So kind of that geometry from ancient Greece has transitioned towards Kepler, and you'll remember someone who knew quite a lot about Euclid, and you'll see how that that kind of flows. From this point, it is suitable to talk about the content of Mysterium Cosmographium, because that's kind of all that happened before the creation of Mysterium. I guess I'll kind of shorten it in that way. Briefly put, Mysterium is the defense of the Copernican system, and Kepler used the Platonic solids in his version of the heliocentric theory to dictate the geometric structure of the universe. And this is where I'm going to stop using vague language, because obviously we need to understand how exactly he's using Platonic solids or regular polyhedrons and what that means for heliocentric theory. I can't just, make the statement. So Kepler realized that the inscribed circle and circumscribed circle of a regular polyhedron could yield a ratio that explains orbits. And I know that's vague, but I'm going to get specific right here. Imagine a cube, okay? A cube has a certain size circle that can fit within it, which creates an inscribed circle, and there's a certain circle that the cube can fit inside, which would be the circumscribed circle. So now you know what those two are. Now, the ratio between these circles, Kepler believed, held a truth about the universe within it. So he continually tried to experiment with three-dimensional polyhedra, the ones that we've talked about. And then he struck gold. How did he do that? He found that if you put an octahedron inside of a icosahedron, inside of a dodecahedron, inside of a tetrahedron, inside of a cube, and put spheres around each of the polyhedrons, it would produce a relatively accurate representation of the planetary spheres established in the Copernican model, which were rather planetary orbits. Now, I know it's going to be very difficult to imagine what that would look like, but I think listening to that explanation hopefully should help you understand what I mean. What I meant earlier with, he used Platonic solids in his version of the heliocentric theory. So yeah, just keep that thought in your head. Now, another thing that he did with the work of Mysterium is he found a formula relating the size of each planet's orbit to the length of the orbital period. From inner to outer planets, the ratio of increase in orbital speed is twice the difference of orbital radius. But Kepler later rejected this formula because it was not precise enough. So that is a little bit of the work that he did with polyhedra that's going to play into some of the later work that he does with orbits and planetary motion. Interestingly, Tycho had some things to say about his work, which prompted Kepler's decision to work with Tycho. So maybe a little bit of reasoning to why he moved to Prague in 1600. So after the work of Mysterium, Kepler worked on Astronomiae pars Optica. I don't think the works were quite in succession, as I will make them seem in this episode, but I'm listing them in chronological order based on when he completed the works. So after Mysterium comes Pars Optica. Not much information can be found about this book, so we can't talk about it too in depth in terms of what he actually wrote in there. But there are some lovely facts listed by our beloved NASA that will tell us quite a lot about what this piece is related to. So in his book, Astronomia Pars Optica, for which he earned the title of founder of modern optics, Kepler was the first to investigate the formation of pictures with a pinhole camera, first to explain the process of vision by refraction within the eye, first to formulate eyeglass designing for nearsightedness and farsightedness, and the first to explain the use of both eyes for depth perception. So that's really all there is to Pars Optica. It's obviously more influential than this kind of description makes it seem, because he literally founded optics. So after that, in chronological order, there is Astronomia Nova, and this is going to be the huge one. This is where the laws of planetary motion come to the forefront. In the research leading up to it, Kepler realizes that there are physical causes to the orbits of planets. So he's steering away from this idea of imaginary planetary spheres that hold up these orbits, like in the Copernican model. So he's looking at Mars as a test subject, and he tries to pick up Copernicus' method to orbital calculation, but obviously we know why that's a little bit error prone. So he wasn't satisfied with it. And then from there, he goes back to the drawing board to figure out how to get oval orbits to work, because I guess he had some trust in oval orbits. He sort of drew influence from William Gilbert, and we haven't talked about him quite that much, but his whole thing was that the Earth acted as a magnet of sorts, and this idea inspired Kepler to theorize that there must have been some motive power that the sun has, which changes orbital paths based on how far a planet is from the sun. So he's getting at this idea of maybe attraction, maybe force, not quite as sophisticated as Newton will make it sound with, the idea of forces, but he's definitely getting somewhere close to that. So based on the measurements of the aphelion and perihelion of the Earth and Mars, I love how aphelion comes up, he created a formula in which a planet's rate of motion is inversely proportional to its distance from the sun. Verifying this relationship through the orbital cycle required very extensive calculation. To simplify this task, by late 1602, Kepler reformulated the proportion in terms of geometry. Planets sweep out equal areas in equal times. His second law of planetary motion. So there's a nice quote that tells you how that came to be. So once he figured this out, and he kind of got these oval orbits to work and finding these mathematical relationships, he went back to Mars, calculating its complete orbit, assuming an oval-like orbit, and using the second law. And he made progress on this endeavor, or as he made progress on this endeavor, the revolutionary law of elliptical orbits came to him, and thus the first law was born. So all planets move in ellipses and not circles anymore. From there, it was only a matter of time that the third law came along, and technically it wasn't, because there was like a ban on Copernican books and a whole lot of conflict that was happening during that time, but eventually we got there. And with the release of his Epitome, or the epitome of Copernican astronomy, which wasn't really about Copernicus, Kepler polished his first two laws and introduced the third. So that's really all you need to know about that. And then I found this really, really cool quotation that gives one of the very few references to Maestlin in Copernicus' biography. Originally intended as an introduction for the uninitiated, Kepler sought to model his epitome after that of his master Michael Maestlin, who published a well-regarded book explaining the basics of geocentric astronomy to non-experts. Kepler completed the first of 3 volumes, consisting of the first 3 books, by 1615 in the same question-answer format as Maestlin's, and had it printed in 1617, and then the second volume, after all that conflict in between, consisting of the rest of the books, came in 1620 and 1621. So yeah, just a couple of facts to elaborate on the creation of the Epitome. So basically it was just astronomy for dummies of the time. And yeah, that's another quote that says that Maestlin has some serious influence, and it's a little bit sad because I went through the research of this episode and Maestlin's name did not come up as frequently as it should have. So, anyways, after this Epitome, most of Kepler's work is dedicated towards the completion of the Rudolphine Tables. He worked on it with Tycho, and there was a brief kind of intermission before he actually completed it in the 1620s. So, yeah, that is the essence of the amount of work that Kepler did. It was quite all over the place, but he did quite a lot of it, and there's a lot of significant things that came out of it, planetary motion. I will leave off, however, with some other facts that are nice to bring up. Kepler was the first to suggest that the sun rotates about its axis in Astronomia Nova. So that's a fun little thing. We saw the development of axial rotation with Earth, that theory, but now we're going to see it with the sun and kind of concerning some theory concerning other celestial objects, which is nice. He was the first to derive the birth year of Christ. Fun fact, if you wanted to know it, you know it. If you didn't, well, you still know it. He was the first to derive logarithms purely based on mathematics, independent of John Napier's tables published in 1614. So there we're seeing a little bit of parallel between astronomy and mathematics. He coined the word satellite in his pamphlet Narratio de Observatis. I'm just going to say that as the abbreviated name because there's a longer name that I will not be able to pronounce. And as for the reception of his work, for Kepler, it was not the best. Several major figures, such as Galileo and, oh god, it's a French name, René Descartes, I hope I'm saying that correctly, completely ignored Kepler's Astronomia Nova. Many astronomers, including Kepler's teacher, Michael Maestlin, objected to Kepler's introduction of physics into his astronomy. Which, I mean, when you hear that fact, it sounds pretty sad. Like, Maestlin wasn't exactly Kepler's idol, but to imagine that someone who influenced and helped you saying that seems kind of rough. And Galileo did receive the help of Kepler at some point, and it was about getting feedback on some of his work, which Kepler happily did, I think. And for him to get nothing in return is also definitely tough. But let's be honest, in hindsight, that means absolutely nothing, considering that Kepler's work was eventually proven by Newton using his laws on universal gravitation, which is known as solving Kepler's problem. So that's a huge positive that almost overshadows all this initial negative feedback. And Kepler ended up becoming the poster child of not only textbooks in the 16th century and beyond, but the scientific revolution itself, which is just like, what more can you ask for? So yeah, that is Kepler. Hopefully you guys enjoyed learning about some of the story behind his findings, because if you're someone who has learned astronomy in one way or another, you've definitely learned about the logistic part of Kepler's work, that is his laws of planetary motion, but it's quite nice to get into depth with how these laws came about, how he broke this idea of circular motion, and kind of using a not so popular Copernican model and turning it into something that we can still refer to today. So yeah, if you enjoyed the episode and you're listening on Spotify, I would appreciate a follow over there. And if you're listening on YouTube, thank you very much for viewing on YouTube. I would appreciate a subscribe. And yeah, that's all I have. Until the next episode, I will see you all later. Peace.